started. Okay, let's get started. Hi everyone. My name's Ricardo Reyno Jr. I'll be your professor for Cal 1 this summer. Let's get started. So today's topics I have for you is just going to be sort of an overview of the things I more or less expect you to know, but that are also something that I want to go through. Obviously, you may come into the class with a couple of gaps, or maybe just you forgot, right? It's been a bit since you've been in school. So this unit, just today's lecture overall, is intended to circumvent that and to try to get rid of that as much as possible. Obviously, I'm not going to go over everything that you're supposed to know, like from pre-cal and below, but this is supposed to be a good idea, more or less. Okay. So today we're going to learn some rules of exponents. We're going to do some factoring ideas, radical and rationalization, and then functions, inputs and outputs. Okay, so let's get started with this set of notes. So hopefully you have these printed out. If you don't, I heavily encourage you to pause the video and go print these out and get them with us for today. Okay. So, let's get started. So, rules of exponents. An exponent is a way of writing repeated multiplication concisely. So, instead of us, writing, a times a n times, we could just rewrite that as a to the power of n. So, for example, if I'm supposed to do 3 to the power of 4, that's an easier way of writing it as 3 times 3 times 3 times 3. Similarly, over here, for 2 to the power of 5, we know that this is just a bunch of times 2's. But how many times 2's are we supposed to have? We're supposed to have 5 sets of 2's being multiplied, right? So that's what this means in general. Now, for here, we want to talk about what do you do when you're multiplying terms that have these powers. So for when you're multiplying terms that have these powers, there is a luxury that comes into play whenever they share the same base. So that same thing that's being taken to the power of. So say we have two multiplying things with the same base, in this case a. So a to the power of m times a to the power of n. That means that as we write them out, we should have m plus n a's that we are multiplying. In this example 3, we can see that we're doing b squared times b to the fourth. This is equal to, 2 sets of b's and then 4 sets of b's. Altogether, how many b's do we have? 6. So b to the power of 6. Now, what's the correlation between 2 and 4 and 6? Well, we know that 2 plus 4 is equal to 6. We can see that same correlation happen here. However, there's a technicality that happens here. Don't forget, if you don't see an exponent, it's an exponent of 1. So for example, if I were to write this out, the first part being a to the power of 7, means that I have 7 a's multiplying. And then I write that last one, that overall, if I count these, I should have 8 a's being multiplied. Over here, similar feat, I have 5 x's and 2 x's multiplying here, so I'm just going to add them, x to the 7. Same feat over here, but with an added twist. The twist is that these guys are not the same base. So we have a set of multiplying terms with powers. And our first, reaction could just be, oh, 7. But the problem is that they do not share the same base. So the answer here is just the expression itself. There's not really anything for us to do here and simplify here. All right, now quotient of powers. So this is a little tricky. It involves division. And when dividing terms with the same base, again, same base, we subtract those exponents. So, I'm not going to show you the rule first. I kind of want to show you these two visualizations first. So we see here that I have 8 A's on the top and 3 A's on the bottom. Well, I can just look here and cancel out those A's like how you would do normally, and then you're left with 5 A's on the top. So that's going to be A to the power of 5 if we simplify it. Now, what's the correlation between 8, 3, and 5, you may ask? Well, 8 minus 3 is 5. Again, over here, if I were to do this as well, I see that I'm only left with 1b or b1, right? Again, what's the correlation between 5, 4, and 1? Well, 5 minus 4 is 1. So, if we follow this as a formula, we can say that a I skipped ahead. If I say that a to the power of m is divided by a to the power of n, saying this is a formula, we would just say we would just rewrite this as a to the power of m minus n. And that's what you get here. Well, I guess for this one, we could take the luxury of doing b by itself, but for right now, it's good to practice writing it with that one. Okay, so next over here, what do we have here? Well, this one's just a little trickier in that nothing really existed on the top. We canceled 3 b's, but we're left with 2 b's on the bottom, so that's b squared. But the top has nothing. Well, technically we know anything times 1 is that anything, so a 1 will exist here. So that's 1 over b squared. And then let's look at example 10. Example 10, our inclination could be 1, but we have to remember they're not the same base. So this expression can only be simplified to the expression itself. Okay. All right. Next off, we have negative powers. So a negative power becomes positive in a denominator of a fraction. So this is kind of referring to this guy over here a little bit, just a little bit, not that much. But if we have a to the power of negative m, then we can rewrite that as 1 over a to the m. And vice versa, if we have 1 over a to the negative m, we can rewrite that as a m. Now, this is the quick sort of like jump to, like we're reviewing. If I'm going to get just a little bit more in depth, which looking at this and I kind of want to, we see here that we can rewrite this as a to the 0 over a to the m. And we know from this rule that that could be written as a to the 0 minus m. Well, we know that 0 minus m, because of the property of 0, is just going to be that minus m, or negative m. And then we're back there at that rule. For here, this becomes a little bit of a simplification issue. Let's see. What's the best way to talk about this guy? Okay. So for this guy, if I wanted to show it, you could believe me, right? Like, obviously, I'm telling you. But I like to show why things are things, and I just don't like to go like the math is math, you know. Um, we have a to the m. We can technically get away with doing a double negative situation, rewriting as a to the negative m, because we agree that double negative becomes a positive. So that's not incorrect in writing it. I'm gonna write a little parentheses actually, just so it doesn't look that ugly. I looked at the screen, it kind of looks weird. Okay. But from here, we can go ahead and treat that as 0 minus a negative m. And then we go backwards, almost like here, where you'd say that's 1 over a to the negative m. And look, we're back where we started. Okay, so in reality, this is the rule. that we should know. This is the why that maybe you don't have to have memorized right away, but you should know that this how, this why exists. This how come, this why because this part that exists somewhere. Maybe you don't have to remember it. It would be helpful to remember, obviously, but like that's sort of the Point Dexter thing of like saying it, where like, well, of course, if you remember everything, but like all of that aside, right? It's good that you need to know that this exists. Maybe not on your notes, maybe not even on my notes, but just somewhere you know they exist, right? You don't have to know it exists in my notes. Okay. Um, let's do the actual simplifications, right? Okay, so from here, we can have initially that if we simplify this, let me use the other guy, excuse me. We have 1 over b to the power of 3. But if for some reason we wanted to just jump to this route, alternatively, we could simply just go, okay, right away, b is 2 minus 5, and then right away we go, boom, b to the power of -3. But we know, because of this rule in particular, that that's going to be 1 over b to the power of 3. Over here, you have a similar feature, but this time I'm going to just copy the rule straightforward. I'm going to write that as a to the power of 3 minus 4. That we know is a to the power of -1. That simply just becomes 1 over a. All right. Let's see. So now we want to talk about what happens when you multiply, or not multiply, excuse me. What happens when you're taking a power of a term that already includes a power? Well, for that, you have these expressions here, right? We have something that looks like you have something with a power, and you have to take it to another power. Same thing over here. Let me bring it to this rule. So this rule simply just says a to the power of m to the power of n. Now think about it like this. If I'm taking all of these segments of multiplying a, and this multiplying a is happening m times, right? And you have this segment again, and you keep having this segment. And you're going to rewrite that segment n times. Well, that means you just have that n times that m amount of a's. So the result would be a to the power of m times n. Think about it like this. If I have, a bag of 5 candies and I somehow increase my amount of bags that I have to, let's say, 6, then how many candies do you have in total? That 5 times that 6. However, we don't want to get confused with the addition and subtraction and the multiplication and division. What I'm doing is a classic just counting example. But we can count the number of multiplications that are happening here. If each of these little bars that I've written have m sets of multiplication, and I'm writing n bars, then I have m times n sets of multiplication. All right. So for here, we can see that visually. We go 3 squared to the power of 4. So we write that 4 times. And then within each of these parentheses, we have 2 sets of 3 being multiplied. So how many sets of this do we have in total? We can just literally count. 1, 2, 3, 4, 5, 6, 7, 8. So I have 3 to the power of 8. But what's the relation between 2, 4, and 8? 2 times 4 is 8. This rule seems to hold. Let's move forward. A to the power of 3 to the power of 2. If I expand this, I have a to the power of 3 times a to the power of 3. Only 2 of them, right? Because it's just power of 2. And then within each little set of parentheses, I have 3 a's multiplying each other. How many a's do I have multiplying each other all together? 1, 2, 3, 4, 5, 6. So a to the power of 6. Again, the correlation, 3 times 2 is 6. This rule holds. Now, power can distribute in this way as well to the top and the bottom of a fraction. If I take the power of a quotient, I have to take the power of both the numerator and the denominator. Don't forget that the numerator is the top part of the fraction, and denominator is the bottom part of the fraction. Okay? Now, keep in mind that at first we learned this trick kind of like how we're doing the powers by expanding. We see that I have, 2 over 3 to the power of 3, and I'm writing that, 3 times. And because of the properties of multiplying with fractions, I can later rewrite this as 2 times 2 times 2 and 3 times 3 times 3. Well, it's not a coincidence. We have 3 sets of 2 on the top and 3 sets of 3 on the bottom. And look what we did. We just technically took that power 3, stacked it on the top, the numerator, and stacked it on the bottom, the denominator. So 2 to the power of 3 divided by 3 to the power of 3. How about we do example 16? Example 16, we can just take it x to the power of 4 over 2 to the power of 4. Now, I think, yeah, I've been avoiding actually multiplying these numbers out. I guess for the sake of technicality, we can go ahead and multiply the numbers out. Um, I was kind of just going with the flow. Let's see. So we know that these 3 to the power of 4, that's just going to be 81. That's going to be, I believe that's 32, but let me double check that. Yeah, okay. Anything else we can simplify here? I'm going down the list. Oh, 3 to the power of 8. We could do that one, yes. So that one becomes 6,561. And then here. Okay, so, oh, all right. That's going to be 8. And this is going to be 80, no, 27. Okay, let me double check just in case. And then, yep, okay, we're good. Actually, let me get white out. Let me get white out and do that real quick. But we can also, the reason why I'm bringing the multiplication up, is not because I don't think you know it. I do, right? You know how to multiply these. But what I want to make sure we know is some simplification, right? How to make things look easier. So for example, here, this looks clunky because we can't really simplify x to the power of 4. But we can indeed simplify 2 to the power of 4. Either doing it out loud in a calculator, etc. And that's going to be 16. Over here, okay, the y out's probably dried out by now, so we got 27. Okay. Over here, we stack the powers on the numerator denominator, so I got 1 to the power of 4 and x to the power of 4. Here, 1 to the power of 4 is just 1 times 1 times 1 times 1, 4 times, but we know that's just going to be 1. So 1 over x to the power of 4. All right. Let's see. Okay. Next page. We're almost done. Okay. Any non-zero number to the power of 0 is 1. Okay. So this is sort of just a trick question. I accidentally did bring it up prematurely here, so keep that in mind if you're wondering how I got from here to here. We see that this, in its technicality, right, is just 1. Because we took 8 to the power of 5, divided it by its exact thing, 8 to the power of 5. Anything divided by that exact same thing, anything, is 1. The only difference is, the only one that doesn't count is a 0. But this leads us to a technicality. If I use the fraction power rule, I should rewrite this 8 to the power of 5 minus 5. Well, that's going to be a to the power of 0. Well, any non-zero number to the power of 0 is 1, which we saw is true here, which we can confirm is true here. So this just sort of helping us confirm it. And we can answer these 3 examples, I feel, with ease, question mark. I don't know, we'll find out. So 9,873 to the power of 0, that's just going to be 1. You could type in the calculator. 5x to the power of 0. Well, we're dealing with a variable. But I did say anything to the power of 0 becomes 1. So 1. How about 2 over 3 to the power of 0? 1. Any non-zero number to the power of 0 is 1. That's just that cut and dry. Okay, so that's all I have for the rules of exponents. This isn't everything technically, right? But it's a good chunk. So let me know if we're gonna try to, eliminate any questions you all have along the way. We're gonna, but if you guys have any other comments, just let me know at the end of the day, right? I'm not a mind reader, and to make this kind of more awkward, this is a virtual class. So it's a bit trickier, but we can do it together if the communication's there. Okay. All right. Now it's time to do part 2, factoring. So, quick factoring idea. Let's start with some simple quadratics. We have quadratics of the form x squared plus bx plus c. Now, some simple factoring will lead us to say that two numbers that multiply to c and add up to b will help us factor these quadratics. Let's start over here. So the rules state that I need two numbers that multiply to c and add up to b. Well, I'm looking at that 12 there, and I have 1 times 12. It's going to be a positive 7, so I don't have to check the negative version of things, but I might as well just do it for at least this first problem. 2 times 6, negative 2 times a negative 6. Oh, sorry, brain fart. And then 3 times 4. Okay, I'm just going to stop. Well, okay, never mind. I won't stop. Okay, I was going to say I'll stop there because I found it, but where's the other one factor away? Might as well just do it. So 3 times 4. 3 times 4 is 12, but 3 plus 4 is 7. So that means I can factor this guy by splitting that part of bx into this 3 and 4. So x squared plus 3x plus 4x is plus 12. What did I do? Just to repeat myself, I split up this middle part into 3x and 4x, which is true, right? We know that 3x plus 4x is 7x. Then I asked myself, okay, well, let me take these first two guys. What do they share? They share an x. So I'm left with x plus 3. And the goal is that you want to factor out something out of these last two, such as it matches what the result after factoring with the first two. So we want to somehow take something out of here that gives us x plus 3. Well, we can see that both of those are divisible by 4. Let's just take a shot in the dark and take out 4. So divided by 4, we got x plus, and then 12 divided by 4, that's going to be a 3. So we have x times x plus 3 plus 4 times x plus 3. That can factor to x plus 4 and x plus 3. And that's going to be our answer. Let's keep it going. We have x squared minus 2x minus 15. Okay, so for here, we have a negative 15. So that means we're going to have alternating sign values. So 1 times 15, but one of them has to be negative. None of those add up to 2. Or negative 2, excuse me. Let's try 2. But 2 times, there's not really, it times an integer gives us 15. And we know that the sum of two things that are integers won't give us another integer. So that's actually wrong. But in the premise of looking for these, we want to deal with some even out factors, right? That's the rule set. What factors, right? And factors typically apply to the integers. Okay. Yeah, that's true. Okay, moving on. All right. Let's see. We got actually the rules probably stay this is well, I'll stay up. Because technically, right, if we take out from an integer, we take out a factor. So for example, 2 times 15 over 2, the sum of an integer and a factor, or in a factor, a fraction, excuse me, will not be an integer. Yeah. I kind of want to prove it, but this is calculus. Let's not do proofs here. Okay, so skip that. Go to 3. 3 times. I'm so sorry for the rants or for the tangents. Okay, we see that for here we got something that adds up to -2, and it's this one. So I'm gonna go ahead and do that. X squared plus 3x minus 5x minus 15. Both of these share an x, so x plus 3, and then both of these share a -5, so x plus 3. X minus 5, x plus 3. Okay, good so far. Now, let's slightly increase the difficulty, okay? Slightly. So example 3 reads 3x squared minus 3x minus 6. Now, the caveat here is that this is not x squared by itself. There's a 3 in front of it. But if you notice, all these three guys do have a factor of 3. So we can rewrite this as 3 times x squared minus x minus 2. And then treat this as the thing that we have to factor, excuse me. So, -2, we check that, there's going to be 1 and 2, and they're alternating. What adds up to -2? This guy. So we have 3x squared plus x minus 2x minus 2. Well, both of those guys share an x, and both of these share a 2, so x plus 1. Yes. And it worked out. We have 3 times x plus 1, x minus 2. That's going to be our factored form of that quadratic. Over here, a similar issue. Or a similar issue. A similar instance with the 2's. So they all share a 2. Let's factor out the 2. 2 parentheses x squared plus x minus 12. Okay. Let's see here. We have a -12. I was gonna see if we can reuse this guy, but we cannot because that's positive. That's negative. But we definitely can just copy and paste those factors. And then just do alternating negative signs. And we have x. So we have 1 for the x, right? B is 1. So this is going to sum up to 1. So we have 2x squared minus 3x plus 4x minus 12. And we're going to see sort of similar thing happen here. 2x, x minus 3 plus 4x minus 3 2x plus 4, x minus 3. All right. And those are all of our answers. Okay. So we're good so far, right? But what about when we don't have that luxury? Well, irregardless, we do have this format of a quadratic where it's an a in front of the x squared with some unknown integer a, right? We can simply just rewrite the rule a little bit to see, okay, what two numbers that multiply to a times c now instead of just c that then add up to b. Okay, so in this case, we're not checking the factors of 3, we're checking the factors of 2 times 3, 6, and seeing what factors add up to 7. Well, Um, I'm gonna stop practicing writing down all the factors. Um, just to save time in the video. But let me know if like that, like if anybody needs an explanation on that, I don't mind. Doesn't matter. Okay, so we see the right way 1 times 6 will add up to 7. So we can just jump that there. We got 2x squared plus x plus 6x plus 3. Out of these first two guys, what do they share? Well, they share an x. So 2x plus 1. All right, now remember the goal. We have to factor something out of here that will make it look like 2x plus 1. Well, that's probably going to be a 3. We can take out here, that'll be a 2x, and 3 out of 3 is just the 1 left over. So, and there we go. X plus 3, 2x plus 1. Over here, we got 6 times a negative 6, which is just negative 36. All the factors of that to add up to negative 5. We have 1 times 36, 2 times 18. Oh, wait, I'm skipping the alternating. Excuse me. Looking for negative 5. Negative 5. Sounds like a bingo caller. Let's see. What was that? 4 times, don't tell me, 9. And this guy over here is going to add up to negative 5. Oops, sorry. So we got 6x squared plus 4x minus 9x minus 6. Okay. Both of these guys are even and they share an x, so I'm only going to take out 2x from here. We have 3x plus 2. And then these guys, they share the negative and they share a 3. So I have 3x plus 2, excuse me. So I have 2x minus 3 with 3x plus 2. Okie doke. Alright, let's keep it going, keep it going. But now we have the luxury here of using both the tricks that we talked about in example 3 and 4 and figure out the factoring quadratic. Because we may see these and be like, oh, it's just an example 3 or 4 situation where you just factor out the common factor that all these three guys share. And you can. You'll get 2x squared minus 2x minus 15. But you still have to do some work. Okay? Now, you can do that and you'll actually get the exact same example. Mm, let me see. Did I? Okay. I made a verbal mistake. I said that this would be not exactly like example 3, but it accidentally became exactly like number 3. So let's go ahead and do this example and then do the version where it's a bit harder, right? Just to show that it's a brute force way either way. All right. So from here, let's see, negative 15. Okay, I already have a list of factors for that over here on this side. I'm looking for negative 2. Oh wait, it's exactly this guy. Oh, so I'm just gonna copy and paste that work. We got 2 times x minus 5, x plus 3. So now the real test. Can we get this example without that? Okay, let me do a different color uh just to prove my point, I guess. Okay. And then let me write here real quick. Use example 2. Okay. All right. We have here 2 times negative 30, which is negative 60. Okay. It's going to be tough, but it's doable. We have 1 times 60. That definitely doesn't add up to 4. Or none of these add up to 4. We got 2 times 30. Gotta be a little closer. We can do 3 times 20. We're closing the gap, but we still need to keep going. Let's do 4 times 15. Again, closing the gap, but not really there. Okay. Then we gotta do 5 times 12. Still not there. 6 times 10. Boom, we're there. We can see that from here. We have the positive 6 and the negative 10. That will get us this factor. So let's go ahead and do that. So I'm just going to rewrite the problem first. And then I'm going to split up. We got 2x squared plus 6x minus 10x minus 30. Okay. Then from here, what two factors do you guys share? They share 2 and an x. So we're left with x plus 3. What do these guys share? Well, to make it look like x plus 3, we take out that negative 10. Not minus plus 3, excuse me. So we get 2x minus 10, x plus 3. What common factors do these guys share? They share a 2. X minus 5. And look, it's the exact same result that we got over here. So now let's do this one the brute force way first, since that was probably my intention when I was writing these notes, but I forgot. Sorry. We have 2 times 24. That's going to be 48. And we got 1 times 48. I'm not going to check the negatives in this case because I know that I need to add them up to be positive just for time as well. 2 times 12. 3 times, what is that? Is that going to be, it's going to be, it's going to be 1. Here, let's do it out loud. 3, 6. What? Oh, what the heck? That's a brain fart. It's 2 times 24 that adds up to 48. Silly. I think I was still looking at 24 maybe. Okay. All right. But yeah, no. That's we can stop. Where can we stop? So 3 times 6, we need to add up to 14. We got to keep going. Let's do 4 times. Now that's going to be 4 times 12. We don't have a 5. Um, we do have a 6, I'm pretty sure. 6 times something will give us that. That's going to be. It's going to be 8. Let's double check that just for funsies. We got. 6 times 8. I was gonna do the column, right? But there's no point. Let's see. What can I do? Um, oh my god, why am I breaking on this? We got 5 times 8 plus 1. And yeah, okay, cool. Just making sure. All right. In that case, we know that that definitely added up to 14. So let's go ahead and move forward. Did I leave myself some space? Yeah, I did. 2x squared plus 6x plus 8x plus 24. And then I'm going to go ahead and do 2x out of the first guy to get x plus 3. And then from here, I need to make it look like 3, but I think, yeah, if you just take out 8, it'll be 8 times 3. Yeah, okay. So 8x plus 3. Okay. So 2x plus 8, x plus 3, They share a common factor of 2, which we could visually see. And notice how if we factored out 2 originally, we would have gotten example 1's instance, which we correctly got as x plus 4 times x plus 3. Oh, I see my typo. I, for some reason, stuttered. Sorry, guys. Let's see. Where's the whiteout? Here's the whiteout. Okay. All right. Okay. We are almost done with this packet. We've talked about rules of exponents and factoring, and then we have one more set of factoring to do, and then we'll jump into the just general function input output ideas. Okay. Let's see. How long have I hold y'all hostage for at this point? 40 minutes? Dang. Okay, I need to keep going. All right. So, factoring quadratics, the difference of squares, right? So, there's a difference of squares, and then there's the sum of squares, but I just feel like difference of squares is a bit more of the tricky one that we're going to probably be using more often than not. Um, difference of squares, just a real quick sort of explanation. X squared minus a squared can be written like this because if we FOIL these out, we get x squared minus ax plus xa minus a squared. Ax and xa are the same thing. These will cancel out, and we're left with x squared minus a squared. So if we were to ask to factor these out, we just simply recognize that both of these terms are squares and rewrite as such. So for example, here, x squared minus 64. Well, I know that x squared is x squared, and then 64 is actually going to be 8 squared. So I can write that as x minus 8, x plus 8. Over here, similar idea with 49, I know it's just 7 squared. X minus 7, and then x plus 7. Okay. All right. Then from here, what we're gonna do is I just want to quickly show you all what if you didn't remember this. Well, you can still use that factoring quadratics part over here. So from here, we're gonna go ahead and just ask ourselves, okay, well, the factors of 49, what factors of these add up to 0, right? Because there's technically 0 x's there. And you would do the math. You would get 149, and oh, you just jumped to 7 right away. Yeah. Either way. Okay. And you don't have to alternate these because it's the same thing. So you can do it like this. We get x squared plus 7x minus 7x minus 49. These guys share an x, and these guys share a negative 7. And you'll get that factor as well. All right. So for the people watching the video, I'm gonna go ahead and actually see if I can pause my recording. Need to I need to eat and dinner's ready apparently. So let me see if I can stop the recording.